In ferromagnetic materials, atoms with impaired electrons are going to act like small magnets. But what's even more interesting, these atoms are going to cluster together, form what we call magnetic domains. Okay, what a magnetic domain is a cluster of these atoms oriented in the same direction. Here, for example, we have a representation of one domain pointing in the direction of that arrow. Here's another one, here's another one, here's another one, and so on. The domains, if we don't have a magnetic field close by, are going to be oriented randomly. And they are going to be affected by thermal energy or heat. So they are going to be actually bouncing around and kind of rotating slightly as temperature changes. Now, when we subject it to a magnetic field, a lot of the domains, not all of them, are going to orient in the direction of that magnetic field. So, in ferromagnetic materials, these randomly oriented domains can orient in the direction of the applied magnetic field. Let me show you that simulation there. Here is the simulation here. Let me move the keyboard away. So if I move the magnet close by, you see how the domains are oriented. I move it far away, and then see here they are keeping that orientation, and actually in real life that's the way we make magnets. The magnets, the bar magnets that you find in the lab, they are made like this, a piece of ferromagnetic material that we place in a strong magnetic field. So when we place them in a strong magnetic field, magnetic domains are going to orient, most of them, in the same direction. And when we remove the magnet, they are going to remain along that direction. They are not going to remain forever, though, because of the temperature, because of thermal energy. Most of them are going to reorient, and eventually that bar is going to lose its magnetism. And the only way to get its magnetism back is to subject it to a strong magnetic field again, kind of recharge it. So if you notice here, these are oriented like this. I reset it, they are randomly oriented. I approach the magnet, and they slowly orient in the direction of the magnetic field. And if I keep this longer, approach it closer, I can get probably all of them to reorient, or most of them. And in real life, it's never going to be all, it's going to be most. This is, I thought, would be an interesting thing. A view at magnetic domains. This is an actual picture. The scale here is 20 micrometers, and you see magnetic domains within a ferromagnetic material. So this particular one, I have no idea what it is, but it seems it's an alloy made up of neodymium, iron, and boron. Okay, now another interesting thing is these domains are not very tiny, a few micrometers, like we just looked here. Now, a few micrometers is not really that small. And actually, when we subject a ferromagnetic material like this one to a magnetic field like this one, the magnetic field is due to this coil here, an electromagnet, we can actually listen to the sound of the domains as they bounce off each other as they reorient. Okay, it's not going to be really music to your ears, but we can hear it. Okay, let's pull this out. Okay, now for example here, so what you have, so as I change the magnetic position, we have the microphone here that's picking up the sound that's amplified, and you can hear it. Actually, this particular microphone is based more on the electricity that's induced here. So it's not really pure sound, but there are different ways of listening to it. Okay, now this particular website, if you are interested, explains to you how you can set it up to listen to the noise of the domains as you change the magnetic field. That noise, we call it the Barkhausen effect.